lens finding in DC2, tools and available datasets. Take it away.
Awesome. Thanks. Thanks everybody, and thanks for the organizers to put together this very nice conference and also putting together a working remote setup. That's very great. All right, so I'm going to give you a talk that is slightly more technical than what we've seen so far. I'm going to talk to you about what I've done for Rubin, for Desk in particular, and the strong lensing science collaboration as well, working on preparing us to find strong gravitational lenses in SLSC in Rubin. So I like to start my talks by showing pictures. Why doesn't it want to show pictures? Okay, pictures of strong gravitational lenses, just to remind us of how beautiful they are, how lucky we are to work on that, and also to explain how they work. But this has been done very thoroughly this morning by all our speakers, so thank you so much to all of you. And of course, this picture should be updated now, because everybody's favorite picture now is becoming this absolutely beautiful, magnificent view of the JWST prospect. I spent the week gazing at that. What I'm going to show you today is not so much on strongly lensed clusters, but more at the galaxy scales. One of my tasks is to help finding these strong gravitational lenses and in all of their flavors. So of course, with all of these images, all the configurations that gravitational lenses can take, they have very various setups. They look very differently from one another. As we've heard this morning, the more exotic strong lenses, like this doubly planed lens to the left, are some of the most interesting ones for cosmology. So we're really interested in building pipelines that are able to find a wide diversity of strong gravitational lenses. These are in the static domain, so it's just a galaxy being lensed by the galaxy. But of course, we're very interested in finding strongly lensed transients, which SLSC is going to be great for that, because we'll have the whole of 10 years to exploit. And of course, for the transient side, we don't always have the opportunity to look for them in the pixel scale, as resolution is not something that we always have, as we've heard this morning with detecting unresolved strongly lensed supernovae. So we need to be able to find them also in the time domain. And so all of these concerns are sort of what I have to integrate into building tools to find strong lenses, to help find strong lenses in Rubin. This is sort of a summary of the lens finding efforts in Rubin. So you see that there are a lot of people interested in running their strong lens finding algorithm on an SST for various science purposes, for various kinds of galaxies of lenses, whether it's in the transient domain or the static domains. And there are a whole lot of search methods, mostly relying on machine learning these days, but not specifically. So we have to try and make sure that all of these sciences are represented. And of course, this is not just for the convenience of people. It's because there is an interest in running varied kinds of lens finders, because each lens finder, as we've shown in this study a few years ago, even if they are very similar in the way they work, these ones were just recognizing morphologies. Even if they work on the same data set, they still find strong gravitational lenses with very different properties, whether it is in terms of Einstein radii, redshift, or magnitude. So these are histograms of different lens finders and what kind of population of lenses they've found in CFH-TLS. So expect each lens finder to be able to find galaxies with strong lenses with different properties, of course. And how do we enable this? How do we get an understanding of how a lens finder is going to be able to find that kind of strong lenses or that other kind of strong lenses? And one way I want to help figuring that out is by using strong synthetic source injection, which is a tool that is being developed by ADM, so by the project in Rubin. And I want to use this on strong gravitational lenses. And the way I propose to do that is to take fake strong lenses, so synthetic generated simulations, and insert them into the actual Rubin images so that we have images that are realistic in terms of their exposure, their noise, the PSF, and etc. While they have the sufficient number of strong lenses so that we can control what populations we're finding, and we can also build training sets based on that. And so the way source injection works is that we take an image, any kind of image, really. Sophie Reed, who's been developing the synthetic source injection pipeline, showed how to inject hypnotodes into DC2 data. So strong gravitational lenses are not a problem at all. And so injecting them into DC2, we should be able, and into the real data, we should be able to build training sets and also build realistic simulations that we enable to get some statistics as to how our lens finders are doing. And so the advantage of running in real data is that we also get all of the spurious detection and all of the realistic images that can pollute our searches. So for now, the way this synthetic source injection of lenses work is that we take a bunch of galaxies from DC2, since we don't yet have data with Rubin, but it will just work just as well with Rubin. We select samples of galaxies based on wherever we think, wherever given lens finder thinks that strong lenses are going to happen. So for instance, this is taken from a Rojas et al. Paper from last year, where we select red elliptical galaxies. These images are from DC2, and we inject strong gravitational lenses in them. And with this, we can build new training sets. One of the advantages, I think, of these, yeah, we can see the difference between the images. One of the interests in this is, of course, to build various lens finders, which will find strong lenses with different populations. Some lens finders will be better at getting point source lights. Some others will be better at getting extended sources. And the idea is that whenever someone wants to search for strong lenses in Rubin, we should be able to inject strong gravitational lenses on other galaxies, so not just the one that already have strong lenses, but all the other ones, or a subsample of them. And then we can run the lens finders on them and get some proper statistics as to how the lens finders are doing in terms of finding preferentially some Einstein radii, some properties of these strong lenses. So this piece already works. I've tried big injection of strong lenses in DC2 with the Gen 3 butler, and this worked just as well on coad images as it works on single exposure images, as you see here. So this is a fake injected, strongly lensed galaxy in DC2 images. And this is 2, but in single exposures, whereas this is correct. This is not the only kind of data sets that we can use in Rubin and in DC2 in what's been simulated so far. So the Lens Sprinkler project, led by Matt Weissner, Nanny Bryce-Lambach, and Danny Goldstein, has generated strongly lensed transients, actually, for the deep drilling fields, for the DDF. So we have about 1,000 lensed AGNs and 1,000 lensed supernovae that live in these deep drilling fields. So far, not of the whole of the deep drilling fields have been processed. Only a subset of them. So we have at the moment 114 strongly lensed AGNs. You can see some example of these. So this is super exciting. I think it's the first lens quasars that we can start to play with in DC2. And so you see the images of the lens quasars here, and you can even see the source galaxy, the host galaxy of the lens quasars. We also have lens supernovae in these data sets. The lens supernovae, there is a lot less of them to see at the moment because, again, not everything has been processed. On my next slide, yes. This is what's been processed so far. So this is the whole of the DDF field. And what you see are all of the strong, supernovae and AGN simulated in the DDF. And so far, we've only processed this small square here, these 4 patches. So this is why we only have 114 AGNs, and there are about 144. There are exactly 144 supernovae in this patch, but only 25 of them exploded during the year 1, year 2 area, which is what's been processed so far. So this is basically the whole span of year 1, year 2 for the DDF. And so here you see all the observations that we have for year 1, year 2 of the DDF. This area here represents about 100 days, and that's where we have observations. We have very dense observations, several dozens per night, because it's the DDF. This actually gives us a little bit of trouble looking at all of the strongly dense supernovae that have been simulated. On this plot on the left, the yellow bars show you the explosion, basically, of the supernovae that have been put in these simulations. And so you see that actually only about half of them end up having points when there has been observations simulated in the DDF. So it's a little bit sad. Half of what's been simulated is not being observed, but it still leaves us with a whole lot of images to play with. These are examples of strongly dense supernovae simulated in the DDF. So as you can see, a lot of them, these ones are selected especially, but a lot of them have very, very, very close separation. It's actually, most of them have close separation because so that we can observe them, they can't be at too high a redshift. So of course, then the lens separation with the lens is not big. So this means that we're going to have to do some work to be able to detect these. At the moment, I can only show these coad images and also, of course, the calyx images, so the single exposures. But Bob Armstrong is working on getting us the difference imaging, where I really hope we can see a little bit better what's going on with these supernovae. Yeah, this is sort of the summary plot that tells me that about half, so 500 of the supernovae that have been simulated have actually points that we can observe and that we can play with in the observed area. Let's skip this. Of course, we can also generate light curves with these. So these are light curves from the DDF, where you see that there are many, many points happening during the same night. This is for an AGN, and this is not based on difference imaging. So I've done flux measurements, but on images that are not deblended. So the lens galaxy is still there. But we can still see some variability in the AGN already. My sort of plan, actually my next task is going to be to do night-based coads. So integrate all the points that happen during one night. So that we can get a better measurement of just the transient itself. And I think this is going to be particularly useful for the strongly dense supernovae, where showing coads over 10 years, actually 2 years, when the supernovae explodes only for a few weeks. Of course, we won't see much of the supernovae. So night-based coads are going to have a lot. So at the moment, I've told you that we've processed only a small subset of the DDF, and Jim Xiang, who's in charge of this processing, is going to process the rest of these fields, going first in the direction of depth, so that we can at least use all of the AGNs and get that much more supernovae, of course. We're working with Bob Armstrong on generating difference imaging. I'm going to make night-based coads, and I intend also to try and make some DIA on night-based coads work. And I think the next steps are really to start building projects around these tools and around these data sets. To start run lens finders, whether they are in the static domain or in the time domain. Investigate the small separation for supernovae, how we can detect them, and we've seen this morning that there are tools to detect even unresolved lens supernovae, so that's really super exciting. There's an example of a project being mounted. So with Georgios Verdanos, we're actually trying to make mock images and see how we can work out injecting strong lenses that also have some measure of micro lensing in them to improve the realism for lens edges. Here are a bunch of links where you can go and get involved and see what's going on in the strong lensing pipeline. And that's it for me. Thank you.
Very nice talk. Thank you. Any questions from the audience?
Thank you, Remy. So this cadence that you only see half of the simulated lens supernovae, is that also going to be real for the deep drilling field, or is it just for the simulation?
Yeah, I think so. I mean, I don't know how set in stone this cadence is for the deep drilling field. I don't know if anyone knows better than me.
So the LSST DC2 simulations were done a few years ago, and at that point, the standard cadence for LSST was something called Minion 1018. It has changed to something called Baseline 2.1. This is better for the wide fast deep, but not terribly different for the DDFs. So you should expect similar performance in the DDFs. And that does mean there will be supernova that just drop on the floor in that region. That's unfortunate, but it isn't set in stone, and we can advocate for it. The place to advocate for it is the LSST PCW that's happening in Tucson in 2 weeks. So this is exactly what the kind of feedback I want is please tell us what we should go fight for. The other thing that may not have been clear, I think, from what Remy talked about, is that the injected supernova and DC2 also have realistic time delays. And we have a bunch of people today telling us about doing time delay measurements. You can do them with these simulations. If you are interested in that, please come talk with me. We will happily help you declare a desk project to do this. It's like, that's my job, is to get you working.
And come talk with me. I'm happy to share. I have a bunch of notebooks on the on this GitHub account. Probably need being updated. But I have a bunch of notebooks that help you actually pull these data and play with these and make the light curves and so on.
Any more questions?
Excellent talk. So I see that you've run some photometry without DIA, and then you mentioned the nightly coads. So I'm taking the opportunity to ask you: would you coad the DIA images? Would you take different fluxes? And then a follow-up question for later. You mentioned the deblender. And do you have any plans in comparing what a deblending tool can do against DIA? Because these are scenarios where DIA can do a very poor job.
Yeah. Yeah, great. Okay. So the first question was night-based coads. Do I DIA and then do night-based, or do I do coads and then DIA? I think I'm not sure exactly, but I know that there are people who have been working on that. So there's help to be pulled. I think it makes more sense to do DIA and then coads. But I think that's definitely something to be investigated. And the issue is, as always, how consistent is the PSF? Yeah, and in that measure, it's actually probably better to do a nightly coad, make sure you get the PSF right and do the DIA. So
okay,
coming back.
What's this?
And then the other question was deblending, which is a topic dear to my heart. I always have a deblending slide. I think that's actually a really good question that I haven't tried, that I actually already could. I definitely think that here difference imaging is going to be doing a better job. In particular, I mean, you need to deblend something. Most deblenders need to know that there is something to be deblended. And in particular, in these images, it's really hard to tell, but there is actually even some things. So I think it's better to rely on alerts that are produced by DIA's images and work from there. Yeah.
My question is on.
Mm-hmm.
We know that for the city project, only going to so doesn't matter. So if let's say you have a very good cadence,
Mhm.
then you have to go out all those bucks. As opposed to applying the DIA, which is something that Kessler, for instance, has mentioned multiple times that's good. It works better.
Okay, great. Yeah, I don't have the answer to that, but that's definitely a good thing to explore. So that should probably become a project.
Okay,
Thanks.
we have a few more minutes for another question. Online, I see Tom. You want to unmute yourself and ask?
Thank you. I had a question about running this all through the LSST
No,
alert
I
screen.
can. Okay.
Can you hear me?
Oh, yeah, go ahead then. I don't see it. Sure.
I wanted to ask, can you run this through the full LSST
So,
alert
so
stream?
Tom Collett asks if we will be able to run the full LSST alert stream on the lens SNE to see what gets thrown away as non-PSI like, non-PSF like.
What gets thrown away as non-BSF?
PSF like.
Ah, okay. I have no idea. Maybe people in the time domain, from my experience, have better answers.
Any comments or follow-up questions? All right, so in that, oh, there's one more.
It's just a comment on throwing away non-PSF like things. A lens transient image pair is a pretty well-defined object. So I'm guessing other people have thought of this before me. Is the scope for us to define a PSF as a function of image separation for lens transient image pairs?
I haven't thought of that before, so I don't have a good.
Yeah, it's just a comment.
But yeah,
It shouldn't be that difficult, should it?
yeah.
Yeah.
Thanks.
Okay, with that, let's thank the speaker again.